Hey everybody, and welcome to the internet. What we're going to be doing in our triple chemistry lesson today is having a look at how the concentration affects the rate of reaction. So this is the next one of our factors that can affect the rate of chemical reactions. As always, to start us off, we've got our starter questions, so take your pick, either up to grade 5 on the left or grade 5 and up on the right. So get those answers written down in your book. I'm just going to give you about 3 minutes to get that done for me. Okay, let's check those answers then. So for those of you doing the up to grade 5, what we were looking at in terms of our pattern is that as the temperature increases, the rate of reaction increases. Now, because that was a describe or our trend, we only need to say what we see. For the grade 5 and up, we had to explain the trend that we see. So what we need to do here, and you can give yourself a tick for each of these points as I give them to you. As the temperature increases, the rate of reaction increases. If you've got that, give yourself a tick first of all. Second tick is for saying that when temperature increases, the particles gain kinetic energy or they gain energy. There's a tick. Next mark is for saying that the particles are moving faster. And then your next mark is for saying that there are more frequent successful collisions. So, add up your scores for me and let me know in the window how you did on that one. Now, hopefully the method that you can see on the screen is familiar to you, because this is the same method that we used when we were looking at the temperature. So we're still going to use our sodium thiosulfate, we're still going to use hydrochloric acid, and we're going to have some crosses on a piece of paper under our beaker or conical flask. Now, what we're doing is recording the time it takes for those crosses to no longer be visible. The key difference between this experiment and the one we did for temperature is, in this case, it's all done at the same temperature. The thing we're changing will be the concentration. So what I've got for you is a little video clip taking you through this experiment, because obviously we can't do this one at home. I did try to see if there was a way we could do it with random items from the kitchen and bits of chalk we can find in our garden, but it really didn't work, so we're not going to try that one. But I do have a video for you to have a little look at.
This next demonstration I'm going to do is one that I've probably been doing for some 20 years. And the first time I saw it performed, I thought, boy, I hope I can do something like that. Because it was so interesting to see chemistry taught with a demonstration and talking. And Dave Tanis was my inspiration. When I saw him do it, I decided I needed to go to more workshops. But this is a kinetics demonstration that I've since used mostly as a lab. It can be done on the overhead projector and all the students can gather data together, or you can have them do it back in the laboratory. It's a clock reaction, essentially. Let me go to the board for a minute and write the equation. We're going to take a sodium thiosulfate, and we've got a 0.15 molar solution of sodium thiosulfate. And we're going to add to that hydrochloric acid. All right, and I've only got the net ionic equation because the sodium and the chloride ions are spectators. This forms solid sulfur, sulfur dioxide and water. This solid sulfur is a colloid. It stays in suspension and it'll eventually block the light coming through my beaker. You may have done this reaction as part of a chemical sunset, because there's a nice demonstration people do when they're putting it on the overhead projector and they can see as the colloid forms more and more. But we're going to do it as a lab, and we're going to be talking about concentration. And what I've done is I have 5 beakers, and the beakers have varying concentrations of the thiosulfate. So in the first beaker, of course, I've just got the pure 0.15 molar sodium thiosulfate, and then I have diluted it along the way. And I would give my students a data table like this and ask them to calculate those new concentrations for the other 4 beakers. We're going to add 5 milliliters of hydrochloric acid, and the students are going to observe the disappearance of an X as that colloidal sulfur forms. So we need to time this, and can I get a volunteer? Jen, I'm going to tell you when to start and when to stop. And I'm going to put the sulfuric acid in here and then, hydrochloric acid, and then, tell you to start and then stop. Start. All right, now I'm going to tell you when the X disappears. If you look from the side, you should start to see the cloudiness on the side. All right, now you're looking down. Stop. Okay. How many seconds did that take? 18.68. 18.68 seconds. All right, and what the students think, I'm not going to do the whole experiment for you, but what the students would do usually, if I have them do it as a lab, they'll do each part. And I always warn them. I say to them, start the last one early, because it's going to take longer for that last one to change. And what we do is we start measuring. We put the other ones in. And they will take varying amounts of time to change, and the kids time them. The last one frequently takes like 3 to 5 minutes to change, and so if they don't start that one early, they'll have some problems, but they will get a sense of the rate. And we do the first one early so that the kids get an idea of how to mark that X. And and they'll just change it. So it's concentration versus the rate. And let me show you what the data would look like for something that I did do in my classroom. We'll do a cooking show approach to this. This is some actual data that my students gathered. And you see that in this case, their initial one was 22 seconds, and their final one was almost 3 minutes. We're going to look at the graph if we plot the concentration versus time. So if I plot concentration versus time, it's not linear. So I talked to the kids about the fact, well, what about rate? If you're looking at rate, the more time it takes, the slower you're going. So it's really an inverse relationship. Let's look at the graph of concentration versus 1/time. So it's easy for kids to do this now with those graphing calculators. And so I show them how to make lists and use the graphing calculator, and they will get a linear relationship for this. You can talk about the fact that this is the concentration in this case is directly proportional to time. If you're teaching a class where you talk about rate constants, you can say this is first order with respect to concentration. Otherwise, you can just talk about the fact that it's an inverse relationship, but it's directly proportional. And you can ask them, well, how could I test to see what the relationship is with the amount of acid? There's 2 reagents involved, the thiosulfate and the acid. We kept the acid constant. Let's see, could you tell me how to alter the experiment? And that would get them thinking about variables that they'd have to hold everything constant, and they except for the HCl concentration, and they could take a similar graph of that. It's a great experiment. It has a lot of extensions. They could even look at the effect of temperature on rate with this experiment. And so I really recommend it to you. It's something that you can do with your classes, and I hope you enjoy it as much as I do.
Before we really go into talking about that experiment in more detail, what I want you to do is have a go in your books at writing me down a definition for the word concentration. So I'm just going to give you about 40 seconds, define concentration in your books. Hopefully what we remembered is that concentration is the amount of solute dissolved in a solvent. So if you didn't get that, make sure you write down that definition for me now. If you did get it right, give yourself a tick as always. I'll leave this up here for about 30 seconds for those of you that still need to write it down. So what we actually saw in that video demonstration was we were actually taking our sodium thiosulfate in different concentrations. Now the acid remained the same concentration, all we were doing was changing the concentration of our sodium thiosulfate. Now the results that she got in her experiment with her group are on the screen there for us. What I'd like you to do then is 2 things. First of all, I want you to copy that table into your book and complete it by doing the rate as 1 divided by the time. So for example, our first one, you do 1 divided by 22.5. Please go careful, it is going to be a decimal place. You will not be doing 22.5 divided by 1 because that would just be ridiculous for hopefully very obvious reasons. 1 divided by the time and fill out the rest of the table. Then what I want you to do is sketch the graph of concentration against time just to show the expected shape. So see if you can just sketch me that little graph, thinking back to what she showed you in the video of time and concentration. Have a go. I'm just going to give you about 5 minutes to get this done. First thing to have a look at then is the shape of the graph. Now I've plotted it here for us on the screen, so just double check, did you get that curve? Now key things that you might have gone astray on here is if you didn't plot your x-axis, which is your concentration, increasing. So if you started at the top of the table and put that closest to your y-axis, then it's going to be completely the wrong way around. Remember, we always start at 0 in our bottom left, or our lowest value, and then we increase as we go towards the right. So we should have that shape graph. If you don't have that, then obviously do a quick sketch for me now, just making sure you label that one as time against concentration. So time is on our y-axis and the concentration is on the x-axis. The second part I asked you to do was to calculate the rate, so 1 divided by the time for each case. So you can see that I've filled out the table there with that right hand column. So just double check and tick any of these that you got correct. Now I've done all of these to 3 decimal places. So our first one should be 0.040, second one 0.037, third one 0.028, fourth one 0.016, and then the final one 0.006. So see how many you got right, add them up, give yourself a score out of 5 for that. Now what I'd like you to do is, we've got the rates there, so if you hadn't managed to calculate them, obviously write them down now. Then what I want you to do is sketch me another graph, this time of concentration against rate. So concentration on your x-axis, because that's the thing we're changing, so it always goes on our x. And then our y-axis is going to be the rate this time. So just sketch a graph to show the expected shape. And again, you were showed this in the video demonstration, so hopefully you can remember what it should look like. Hopefully we got a nice straight line. So you can see here, this is what we would expect for our rate against concentration. So as our concentration increases, then the rate also increases. And it does so in a linear relationship here. So if you didn't get that, obviously quickly sketch that out for me. I'll leave this up for about 30 seconds. So what we've got on the screen now then are our sentences for our conclusion. Again, I've given you 3 keywords at the bottom. That's for the second part. The top one, I want you to finish off that sentence using your own words. They're not at the bottom. The 3 words at the bottom for 3 spaces at the end of this. So I'll leave this up here for a couple of minutes. Finish that off for me using the words at the bottom and your own words for that first sentence. Okay, let's make sure we got those correct spaces. So I found out when we increase the concentration, the rate of reaction increases. Words to that effect is what we need in there. If you got that, give yourself a tick. This is because when the concentration increases, the particles are more crowded. Give yourself a tick. This means they will have more frequent, successful collisions. Now, hopefully you've noticed that this phrase is back again. We saw it in our temperature. More frequent, successful collisions. This is kind of your go-to phrase, if you like, when we're talking about any rates of reaction explanation. So when they ask you to explain why increasing the temperature, increasing the concentration, whatever it is, increases the rate of reaction, more frequent, successful collisions. Those are the 4 key words to make sure you've got. So just leave that up there for about another 10 seconds, just in case you need to fill out any more words. One of the key things we need to bear in mind is that the reaction won't continue indefinitely. Reactions will come to an end when the limiting reactant has been used up. And what we can also say then is that the amount of product that we will produce is proportional to the amount of limiting reactant. So if we double the amount of limiting reactant, we double the amount of product. If we halve the amount of limiting reactant, we halve the amount of product. And this is one of those questions where if they ask you what doubling the amount of limiting reactant does, don't just say it increases the amount of product. Because if they've used words like double, halve, etc. in the question, they're expecting you to then use those same comparative terms. So just go careful not to throw away easy marks there. So make sure you got those 2 sentences written down in your books. I'll leave that up there for about another 30 seconds for you. So now we've finished looking at concentration, we need to consider what happens in different pressures. So when we're thinking about reacting gases. So what I want you to do is just write down in your books what you think will happen to the rate of reaction when we increase the pressure. Just 30 seconds to do that for me. Now, what we actually find is that if we increase the pressure, then the particles in those gases are becoming more crowded. If the particles are more crowded, then they're going to collide more frequently. So we see a faster rate. So make sure you've got that sentence written down in your books. I'll just give you about 40 seconds to get that done. Just a little animation to show you this then. When they're flashing, they're reacting. So this is under low pressure. They've got plenty of space. They're not particularly crowded. So it's taking a while for them to actually react. When the plunger moves in, then we're increasing the pressure. The particles are more crowded and they reacted before I could even finish that sentence. So let's finish off today's lesson then with our usual plenary questions. Up to grade 5 on the left, grade 5 and up, your question is on the right. So I'll leave this up for about 30 seconds so you have a chance to answer it, but you're probably going to need a bit longer. If you do, then just hit pause now. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.